Hey everyone, welcome back to Black Box Engineering. This will be my first course video. As I said, most of the time I'll be using LTSpice. It is a free circuit simulation program made by a company called Analog Devices. It is available, it's free, and there's really basically no limitations. There's a ton of user content and tutorials that teach you how to use the program like step by step. It's actually quite an incredible piece of software. So in any case, all you have to do is go to analog.com and go to their design tools and calculators and find LTSpice, or you could just Google LTSpice. You just download it, and there's like a couple libraries that you have to wait for the first time, but every once in a while new spice models get imported so that you could let's say you want to know how a particular integrated circuit works. There's all sorts of free models that get imported from time to time. Basically, people do the work for you for more complex parts. So anyway, this is where you download the software. The basic layout kind of looks like this. You can just start a new file, and you usually can find your basic components up in the top here. This is so that you can run your circuit. There's a couple of different modes. This is for wires, this is ground, resistor, capacitor, inductor, diode, and then your various list of components that you can also experiment with. So, and you can even create your own little sub-circuits if you want to. So in any case, so what we're going to do here is I'm going to go over the basics of circuit laws that you should learn to do some circuit analysis so that you can actually start experimenting with your own physical circuit. I know that a lot of people know the basics are, but there's just certain things that don't quite get covered in class that I think are important. So what I'm going to first do is I'm going to mention a couple of things here. First of all, if you don't know much about voltage sources, I'm going to have a little info card in the top right. I made a video about misconceptions on voltage sources. The very basic gist of it is that when you get taught circuits for the first time, all that you really know is like those benchtop ones that you adjust with dials. This symbol could be a lot of different things. You can have a digital voltage source, like from a computer, microchip, something like this tiny. You can have an analog voltage source, like from some kind of like a pulse width modulation output, where it's just like a square wave, a triangle wave. You can have a AC signal, which is like a sine wave. That can come from various spots as well. This is just a stand-in symbol for almost any voltage source that you can think of. And then we're just going to start with resistors because that's the easiest to understand. The very first law that anyone really should keep in mind is voltage equals current times resistance, which is Ohm's Law, or V equals I times R. I'm not really going to go through derivation because I think that kind of wastes time. I need to get rid of the Grammarly plugin. I don't need it for simulation. But there's also the power equations. So P equals voltage times resistance. or power is equal to current squared times resistance, and I don't have a symbol for the power of 2, so usually people use a different letter than I because it can get complicated with imaginary numbers, but we're not going to talk about that now. So these equations are like your bread and butter for almost everything. There are a little bit more complex equations for like inductors and capacitors, but that'll come up later. All that we need to know is that voltage is equal to current times resistance, and these two equations are for power. Power equals voltage times resistance, and power equals current squared times resistance. It'll all make sense when we actually start plugging in values. So right now, the most basic circuit that we can hook up is just one little resistor hooked up to a voltage source. Now, this won't run at all if I tried to, because, well, one, we haven't defined what the resistance is, and we don't know what the voltage is either, so, and it doesn't have a connection to ground. So we're going to get some errors. So I'll go over this command soon. But anyway, let's say that we want to work with a 5-volt source. And we can just plug in a DC value of 5. So there aren't going to be a lot of actual voltage sources that are 5. Some digital ones are, but let's just have a stand-in of 5, just as an example here. And then let's say that we just choose a resistance, and resistance is measured in ohms. It's how much the circuit will literally resist flow. And then, so this could be any value from milliohms, less than that, regular ohms, mega ohms, giga ohms. It's just let's just make it easy and make it also 5. So we can, it's useful to figure out what your current values are before you run your simulation or experiment on the bench as to what components you're going to use. So instead of depending on simulation alone, it's kind of cool to know how to calculate things. And right now we can kind of ignore the nonlinear portion of this, but we ignore this and just focus on time domain simulation. All that this is saying is that we let this circuit run for 5 seconds based off of the parameters that we give it in the actual values. And you can change different steps here, but the very basic thing that we need is a stop time. So let's just go for 5 seconds. And now we can bring up the equation again. So V1 is going to be 5 volts. So 5 volts is equal to resistance times current. We don't know what the current is, so let's just label that I. And we're timesing it by the resistance value of 5. So this should just give us a basic 1 amp, and that's the base value for current. Think of it as it's not really a rate of flow, but it's more like the strength of the electrons moving through your conductive material. 1 amp is actually kind of high. An amp or more is going to be, it all depends on what you're talking about, but in the world of like experimenting with small values, 1 amp is actually quite high. It all depends on what you're talking about. In the real world, 1 amp is not really all that high. You actually get some applications that are like 50 amps or 60 or 70. Those are the more dangerous high power applications. A good way to give an idea of how much that actually is. Just trying to give a good example here. Oh, yeah. So, like the combined electronics of, I'd say, a good way to compare it would be maybe a charging circuit for like a phone or something. You don't need all that much amperage to charge basic electronics. Some are higher power, like 5 amp, but that's pushing a lot of current through wire. But not a lot of things actually, like small electronics typically don't take that much. It all depends on what you're talking about, of course, but yeah, like a charging circuit would be maybe an amp, maybe 2, 5 at the most. Again, it all depends on what you're talking about. But when you're talking about like really high amperage, I do know that electric vehicles, they can draw like 500 or more amps. It's an insanely high value because you've got electric motors, which are very power hungry. You've got your voltage controller or regulator that takes amperage. You've got all your subsystems like your navigation, your headlights, and other your safety systems. But the four, well, it depends if it's 2-wheel drive or all-wheel drive or whatever. But the majority of the power that is delivered in an electric vehicle, just as an example, that draws the most amount of current. And I do know that all the things combined, it can be up to like 500 amps or more. It all depends on the electric vehicle model, but yeah, current can get insanely huge. Where it gets really dangerous is like transforming stations that you go, if you've ever gone like out of town and you see those huge those huge transformer banks with these, like the small grid thing that you see outside of the city or something like that. That's like kilo amp levels. Touch it and you die, basically. So yeah, it all depends on what you're talking about, but 1 amp in terms of what we're doing is small. Or no, sorry, 1 amp for what we're doing is kind of up there, but everyone kind of just starts with that. Having the same voltage at the same resistance will give you 1 amp. That's really all that we need to get out of this. So anyway, so if I actually were to run this and show, oops, right, you need a path to ground. Now, up in the right hand corner, I'll also link a video to common misconceptions, or not misconceptions, but exactly what is ground. But usually you hook it up to the negative side of the battery or whatever power supply that you have in your brain, and then this will actually run. So if we just let this run, if we hold down the Alt key on wire, because this will just get, if you click a wire, it'll just give us voltage. Right now we don't have any other resistances in line, so the only voltage that you'll see across positive and negative is going to be 5 volts. So if you just click one side, you're going to get 5 volts regardless. So as I said, if we hold down Alt across on the wire itself, we should get 1 amp, as this says. We can also just click the resistor and it'll give us the same value. Now, coincidentally speaking, the amount of watts that the resistor consumes, and this usually is in the form of heat, by the way, happens to be power is equal to voltage, which is 5, times current, which is 1. So your power is just going to be 5 watts. So if I hold Alt, you get a little thermometer here, and you see that the value is 5 watts. We can also run a calculation to double check the I squared R value. To do that, we can right click this and delete the trace. We can add a trace of our own, and let's say that we want hold on here, might have to do a little bit of algebra. Let's see, so V equals IR, we know that, and if we want resistance, we can just take V over I, so that would be, let's put parentheses around these. Sorry about that. I always forget that some like shorthand tricks don't work. Oh, I did the wrong thing squared. Dang it. I squared. Power times R, which is V over that value. There we go. Sorry about that. So yeah, this is the second way to get the same value as the current. So yeah, this is the same thing as taking this current, squared times the voltage divided by the current over the resistor. Yep, same value. Okay, so yes, the resistor is consuming 5 watts of power. As of right now, the best way to think of a watt, just conceptually speaking, think of a light bulb. You see, like like an older light bulb, 50 watts is not super high. 100 watt or 120 watt was a lot brighter back when light bulbs were just basic coils. So 5 watts is very small. Anyway, so yeah, that's just like a basic equation for doing a simple 1 resistor circuit. So if we add more, let's say that we increase our voltage by 2. No, sorry, not. If we double it, we're going to get 2 amps, because V equals I times R, so 10 over 5 is 2. So this should get 2 amps. If I hold, yep, 2 amps. So 2 amps times the voltage would be 20 watts. Yep. So we've went from all the way from 5 watts up to 20. That's 4 times as much. Neat trick about LTSpice is that you can kind of get an idea of how to scale your idea by ramping your voltage. The way that you do that is you can use your tools here to do this. So switch over to DC sweep, and we're gonna sweep V1. We're just gonna do a linear sweep. We're gonna go from 0 to 10 with increments of, I don't know, half a volt, I guess. And if we hit run, we should be seeing a linear increase from 0 to 2 amps, but power increases logarithmically. If I were to change the, let's see, I always forget how to do this. Did I scale the right thing? No. Oops. Sometimes you have to rerun the simulation. Maybe it would be the voltage? Yeah. So if I change the voltage into a logarithmic scale, it kind of looked weird when I scaled the wattage that way. The current, of course, now looks a little bit more curved, but that's because we manipulated the x-axis. It's more pronounced with the wattage because wattage increases faster than the current does, because you're taking the current times the voltage. So yeah, at a simple, let's just trace this. If you click the trace of your choice, you can kind of pick certain values. So back at 5 volts, I think it was, yeah, 5 volts gives you 5 watts. 5.5 volts gives you 6 watts. 6 volts, I'm confusing myself here, gives you 7 watts. And then it just keeps going up and up and up and up and up. So that's why it's a much more steep change. And of course at 10 volts it's 20 watts. So it does not, power does not increase on a linear scale. It increases on an exponential scale. So, and you'll notice that at very low values, like let's say 1 volt, you're going to get 308 milliwatts. So that's 0.308 watts if you were to use the same conversion. So if your voltage source is equal to or greater than, your power is going to increase like that. If it's less than, it's going to be like let's say 4 volts. Oh wait, I'm still on DC sweep. That's not going to change anything. Now, since V equals IR, so 4 over 5 would give you, I can't do that math in my head. I'm not great at it's 0.8, so it should be 0.8 amps or 800 milliamps. Yep, 800 milliamps. So 0.8 times 5, which is only 4 watts. Or, no, did I not calculate that right? Oops, I multiplied by the wrong value. 4 times 0.8, 3.2 watts. Yep. Is my scale? No, it's not. Yeah, so 3.2 watts. Okay, so yeah, this is like the most basic thing that everyone starts with is learning voltage equals current times resistance. And the rules get a little bit more in depth if you start adding parts to your circuit. It all there's the concept of series, parallel, and a little bit more complex combinations of those together. So I don't know how modular I want to make this, but I think just starting it at a very basic understanding helps a lot. Let me grab one thing here. I may as well disassemble my tic-tac-toe project because I don't use it anymore. So I wanted to talk. Maybe that should be the next video. We'll see. Give me a second here. What time I retired this? You cannibalized it for videos. Look at that mess of wires. That's a mess of a thing I had to hand solder there. Alright, and then there's a huge rat nest inside of that. Let's see. I just wanted to show you before I ended the video how tiny these parts can be, because pictures on electronics component sites are super zoomed in, but they are tiny. And I think the next video will be kind of a small one, because there is a concept that not many know of, is how do you select these things? Look how tiny that is. It's itty bitty. It's like barely bigger than my finger. So when I guess the lead-in that I was gonna talk to, or that I was gonna explain for the next video is, so this little piece that everyone starts with, it may not be obvious to a lot of people in a simulation or drawing out a circuit. You don't start with any limitations. Everything that you get shown in class is an ideal part when there's no internal resistances. There's no, like, this battery or whatever the voltage source is, I just like to call it a battery. Like, it's completely ideal. It has no losses whatsoever. In the real world, I guess you could say maybe a 5 milliohm resistance. So let's say if I wanted this to be, I guess, a little bit more realistic, let's say that there's a 5% tolerance on this too, and then if I ran this, you would no longer get 5 watts. Actually, you would get 4.99 watts. It's because all batteries or power sources or whatever, well, yes, even like highly engineered power sources are going to have an efficiency limitation to them. There's no such thing as a perfect power source. Batteries can kind of vary. 5 milliohms is kind of like a guess. The reason that it's just slightly under 5 watts is you have to add 5 milliohms would be 0.005. Actually, let's do that really quick to end this video. So 0.005 plus 5. So these, since this battery is in series, meaning there's no other components in line, I guess it's technically in parallel too, but for the sake of simplicity, it's series. These add up in resistance, so you take your 0.005 plus 5, which is 5.005, and then you take your 5 over 5.005. You get 0.999 amps, which, oops, I am still in run mode. Let's see if that's right. Yep, 999 milliamps. So if you take your 999 milliamps and you multiply it by the voltage again, you're going to get 4.995 watts. So this is actually more realistic, I guess you could say, than this is like how it would actually kind of show up, and that's why you don't usually see an exact voltage rating on many, or it depends on like if your multimeter has a certain tolerance on the voltage levels and all that, but I would assume that a regular voltmeter would probably give you 1 amp, or very, very nearly 1 amp. Again, it all depends on the quality of the multimeter or whatever you're using to measure. There are controlled ways to get the voltage that you need, but you're still going to lose efficiency somewhere. So, in an ideal, or in the engineering sense, that's why you usually start with a higher voltage than what you begin with. Let's say that you plug in your computer, just as a very basic example. That takes your 120 volts, it converts it into DC through a complicated way, through your power supply. Your power supply, let's say it produces 19 volts. 19 volts is pretty typical. It kind of varies from computer to computer. Computer nerds get mad at me, whatever. Let's say that 19 volts is the nominal, like the regular reading. That 19 volts will be used for a bunch of downstream processes so that you can get your exact voltages, but you're going to lose every component that you add. You're going to add stress to the system, so that 19 volts can only be regulated or kept at 19 volts up to a certain level. And that all depends on what each little component draws. Everything adds all up together in their various combinations of series, parallel, whatever you have it. That's why power supplies have a current rating in general. So let's say that your computer takes 200 watts, 250 watts, I don't know. And let's say that your setup is very nearly pushing that. Maybe even more. But if you go more, you typically burn out your supply. But even a little bit. I can get into that later. But let's say that you are very, very nearly 250 watts. You might see some voltage dips because nothing upstream is perfect and nothing downstream is perfect. That's why 19 volts is called like a nominal rating. And it actually might fluctuate between 19 and a little bit less than 19, maybe a little bit more than 19. It all depends on how the power supply works. But if your power is unstable, it may be because it's not regulated properly. There might be something broken in your system. But some power supplies are designed to start derating a little bit if you start pushing that maximum rating to its absolute maximum. Okay. In any case, it all depends on the complexity of the power source. So, but you can get fluctuations in a complicated power supply because of the various loads. It's all about how the regulation circuits are designed. But yeah, it's a little hard to explain. I like to add these little things that come into play for more complex designs. So if you have any questions, please let me know. Like, comment, subscribe, and remember, think outside the box and stay wise. See ya.